Let us do the simulation to the common source amplifier using Cadence Virtuoso. This is my schematic window. This is my schematic window where on which I have to take my circuit. I have to give the instance and I have to select my PDK. So 45 nano PDK, and I have to select a NMOS transistor 1V, and I have to pick the transistor. This is the basic symbol for the MOSFET and MOSFET, and I have to do the configuration. As per the configuration, I have to give input at the gate terminal, and source terminal should be common for the input as well as output, and from the for the drain terminal I have to connect a load across which I have to take a output. So let me connect my input. The input I will be taking from the analog library VDC. Let me take, and V sign also let me take, and let me take ground also. I'm taking resistor from the analog library itself. Actually, it has to be taken from PDK itself, but I'm taking from the analog library. So a generic resistance that I am using it here. Let me do the connections. Source is common, and input is applied at the gate terminal. So let me give the label names for the each and every port. This is my input port, and let me give the label name for the output, and VDD. So from the DC voltage source VDD is generated, that same VDD will be supplied over here. This is biasing. This is nothing but biasing. So which you are applying it over here. So this is the configuration of the common source amplifier, where I have to give the input and where I have to collect the output. So how many times that input signal is getting amplified, that's what we have to calculate theoretically and practically. So theoretical values and practical values matched, our simulation will be completed. We have to prove that the theoretical calculations and practical calculations correct. And before we get the theoretical calculations, what I do is I will be explaining you. I'll do the analysis and I will be deriving the formulas for the calculation of gain, and the same gain will be observed on the simulator then. So as we know, Common source amplifier, the circuit diagram which we have already, where the input is applied with applied at a gate terminal. Input is applied at a gate terminal. This is my gate, and the output is taken across the drain terminal. This is my drain terminal. This is my output. This is my V output. This is my V input, and source terminal. This is my source terminal. It's connected to the ground. This is the basic configuration of the common source amplifier. Load is connected, RT is the load. So now this circuit diagram has to be analyzed, and we have to do the analysis with the circuit parameter called gain. We have to analyze this configuration, we have to analyze, that is through the small signal AC equivalent circuit, that is through small signal AC equivalent circuit. So let us draw the small signal AC equivalent circuit. So let us do the theoretical calculations first. When we do the theoretical calculation for the gain, so let me take the parameter gain. As we know, the gain is nothing but a V output by V input. V output by V input. So we have to get that V output by V input, where V output will be taken across the drain terminal of the amplifier. V input is applied at the gate terminal of the amplifier. Source terminal is common because it is a configuration says that it is a common source configuration. So common source is common. So here this is nothing but drain, this is nothing but source, this is nothing but gate. So as this configuration which we have to calculate the gain, what we do is we will be making a small signal AC equivalent circuit. So this is the small signal AC equivalent circuit, where in the small signal AC equivalent circuit, let me take the transistor small signal model first, and let me connect with whatever the circuit connections that I have it in the schematic, where gate is connected with the V input, and drain is connected with the V output, and source is connected to the ground. Source is connected to the ground, and the drain terminal is connected to the V output. Also a drain terminal connected to the VDD. But in fact, when we do the AC equivalent circuit, the VDD has to be grounded. So when VDD is connected to the ground, where the drain terminal is connected to the ground through RD, let me make a connection over here. This is RD. So from this AC equivalent circuit, let me get the value of the gain when I do the approximation of this one, because it is the maximum I consider. So this is maximum, so that RD, when it is considered as a minimum, so it will be becoming more dominant, so most of the current will be conducted into this one, so I neglect this one. So now let me do the calculation of the current which is flowing into this one. Through that, let me calculate the V output. V output is nothing but there will be GM times of VGS current will be conducted in the opposite direction. So that much current into GM times of VGS, that much current into the resistance of the particular branch is RD. This is considered as the output, and input is nothing but whatever the input you are applying across the VGS, that will be your input VGS. So this one get cancelled, so that am I getting the gain value of GM times of RD. So this is the calculation of the gain. This is the calculation of the gain. So RD is the gain, like we are getting GM times of RD, where RD, I'm getting the gain equal to minus GM times of RD when R output is neglected. If it is not neglected, my gain value will be minus GM times of R output comes parallel with RD. So it is our choice. R output can be neglected or will be considered. So in mostly R output, when it is very high, so parallel of small resistance, it will be a equivalent value of small, so that RD will be coming into the picture. So if RD value is very large, when compared to RD value is large, which will be near to the value of R output, so then RD should be considered along with R output, right? So this will be the formula of the gain, that theoretically I can calculate the gain through this formula, and practically how you do it, that will be observed on the simulator. And before go to the simulation, So we have to know something about the circuit once. So in the circuit diagram where choice of, I need to know the choice of length and the choice of load resistance RT. So there is no chance that we can keep that any value of the L and any value of the RT. So there is a range of load resistance and there is a range of channel length that we have to choose. We have to choose. So before you do the simulation, we let us have a discussion on. Yes. So theoretical calculation of the gain minus GM times of RD or minus GM times of R output parallel with RD that we have identified. So now let us see that practically you will get the same through the simulation. So before you do the simulation, we have to adjust that all the circuit parameters once. So what kind of that input we have to provide, what value of RD we have to provide, what value of length and width that we have to provide, we have to clearly know about it. So let me discuss about that also. Let me have a discussion on that also. Yes. So if you see this one, choice of the length. So here let me explain it about the choice of the length. So choice of the length. So length of the device, if it is very small, short channel device if I consider. If I consider the short channel device, length of the device is minimum. Length of the device will be minimum. So then lambda value of the device will be maximum. Lambda value will be maximum. So then what happens? As we know the current equation is 1 by 2 mu COX W by L times of VGS minus VTH. So this is the actual current which is flowing across the drain terminal. This will be the current which is flowing into the drain terminal of that much. Right. So it will be flowing that current. It will be conducting the current of that much. When gate has the total control. When gate has the total control. So whatever the gate voltage that we are applying it over here, that itself controlling the total flow of the current. This is the channel where the current of ID has to be conducted. If the current ID, if it is controlled totally by the gate, then the current equation is this one. But there is a channel length modulation effect will be there for the transistor. So we have to consider that. So what channel length modulation is saying is 1 plus lambda times of VDS, right? This will be the factor also will be added so that drain current is not constantly changes with respect to VGS. It is also changed with respect to VDS. There are two controlling factors over there. VGS is the one controlling factor and VDS also another controlling factor. So if any one of the parameter changes, that ID will be changed practically. That will comes under the second order effect of the transistor. So now the moment when lambda is maximum means when we are taking that length of the device is very minimum. So if the lambda is maximum, so VDS will be more dominant. So my ID is totally controlled by the VDS. So then that moment what happens is the control of the current flow that has been controlled by gate terminal as well as drain terminal. So that is the problem that we'll be facing over there, but we'll be getting the advantage as when the W by L of the device, where length of the device is small, so W by L quantity will be very high. So when the W by L quantity of the transistor is very high, it will be conducting the drain current is maximum. If the drain current is maximum, the electrical node which is connected to the source, where I consider this one as a output, where I consider this one is output, V output, it will be getting the logic 1 immediately, because that because like large amount of the current will be conducted, so that the capacitor will be fastly charged, so that I will be getting the logic 1. So in the similar way, if I keep another transistor where W by L of the transistor if it is very high, so that transistor also conducts the more current so that the capacitor will be discharged. So what happening is I will be getting logic 1 also, immediately I will be getting the logic 0. So at what rate I will be getting the logic 1 and logic 0s, so I will be getting the high speed, I will be getting the high speed, so we call that one as switching speed. When we have high switching speed, the particular system will be working at very high speed, so high speed design of digital circuits will be possible. So when we are expecting high speed and we don't bother about the control, either gate control or drain control, whatever maybe we have, we don't bother about that, then this kind of things will be more apt, that will be for the digital application. So now I can say when we are making a digital applications, when we are making a digital applications, when we are making a digital applications, my requirement is speed. I don't bother whether the train is controlling and the gate is controlling. So only the ultimate requirement that I have is I need to get the one and zeros at the output at a high speed. In that in that requirement point of view, I have to choose the length of the device should be as minimum as possible, so that short channel devices will be more apt for digital applications. But where in the analog applications, when I'm making the common source amplifier, which will not be the case. So now let us go with the analog applications, analog applications. When we are going with analog applications, there should be a linearity, should uh, the linearity of the there should be linearity with respect. But where in the case of digital applications, for the sorry, but where in the case of analog applications, but where in the case of analog applications, but where in the case of analog applications, there should be linearity with respect to input. The output should be linearly changes with respect to input, so the drain current should be controlled by the gate. Without that, practically we cannot get the application. So id should be mostly function of the vgs, so there should not be much dependent on the vds. For that we have to make sure the lambda should be as minimum as possible. So lambda should be minimum as possible. For that sake, I have to make sure that length of the device should be maximum. So I have to choose the length of the device should be as maximum as possible, so that lambda will be minimum. So channel length modulation can be minimized. So we can reduce the effect of channel length modulation through keeping the length of the device maximum. So this is the choice of the length, and also we have to discuss about the choice of the RD. So if I have the RD value 1 kilo ohm, 2 kilo ohm, 3 kilo ohm, so whatever the value of RD, if you keep it somewhere around 20 kilo ohms, if I'm keeping it over here, will there any problem, or without having any problem will be getting the simulation results or not? That's what we have to discuss. So when we are keeping that RD, there is a problem with the transistor functionality is when the transistor is expecting gm times of vgs current. So gm times of vgs current approximately, when it is a small signal model, approximately is this much. It is also nearby of mu cox w by l times of vgs minus vth. Because we are keeping the length of the device is very very high, like we are keeping, if it is a 45 nanometer technology, we are keeping the length of the device is 1 micro. So very high value of that l value I'm keeping. So I'm neglecting the channel length modulation, so I'm not considering this factor, whatever the lambda times of vds factor that I have, I'm neglecting right now. So now Gm times of VGS or of mu COX W by L, VGS minus VTS, this much amount of the current is expecting, let us suppose. So this value it's around 20 microamperes. For example, I'm considering it is 20 microamperes. So now my biasing circuit where I'm keeping 1.8 volts supply and RD I'm keeping 1 kilo. So with this, it is able to generate the current. If it is able to supply the current of 40 micro, let us suppose. So now the process here is the terminal where the node over here which will be supplied with more current than the expected current of the transistor. So transistor is expecting 20 micro, it is supplied with more than that. So then the transistor will be operated in the saturation, right? So we have to make sure the transistor will be operated only in the saturation when when the expected current of the transistor is this much should be right less than the less than the current given by the biasing circuit. The biasing circuit is not giving that much current, right? Then transistor will go into the linear. So here it is the main criteria where my transistor need to be operated in the saturation region if it is for the analog application. If it is the digital application, I don't have any problem. I can make the operation in the linear also. My transistor may be operated in the linear also. For the analog application, as I'm saying, for the analog application, my transistor should be surely working in the saturation region. For that, I have to protect my device not to go into the linear. So how I can protect? So there is the mechanism that through the RD network, whatever the current it is pumping or current which is passing, it should be greater than the amount of the current he is expecting. That's what we are discussing. So when we are keep on increasing the resistance over here, as we are increasing the load resistance RD, so the current which will be pumping into the device also will be limited. So as the resistance of something where it comes, right, if it is the value, it comes to the 19 micro, so here it is 40. So like that, it is value of the current, drain current, it is reduced. It is 30 micro. So over here this one 19 micro, let us suppose. So the moment when it comes to the 19 micro, so he is expecting 20 micro. So there is no proper balancing that expected current more than the current which is pumping. So the transistor cannot work in the saturation, right? Transistor will go into the linear. So here this is the condition where my load resistance cannot be maximum, so that I can get the maximum gain by the formula as we know, right? Gm times of RT. This is the gain for the common source amplifier. So as you are increasing that load resistance, you may get the maximum gain. You may get the maximum gain, right? But the problem with keeping the value of RD maximum in the requirement of getting the maximum gain, we will be facing the problem that transistor may go into the linear. So further we cannot get the maximum gain, right? So these two, the choice of the length and the choice of the RT, we have to consider, we have to keep it in the mind while you are doing the simulation. Let us go into the simulation once again. Let me apply the value of the DC voltage source 1.8 volts and load resistance. I am keeping this one as a parameter RD, and the length of the device and width of the device also I'm keeping it as a parameters itself. Q. So length of the device is L, width is W, and here DC voltage source, and we have to make sure the two parameters need to be mentioned for the transient analysis. One is DC voltage source, there is a biasing voltage also need to be given. So otherwise the transistor, as we are discussing, the transistor may go into the linear or saturation, but the main criteria we have to bring it out of the cutoff. So for that, channel has to be formed. For that, there should be a sufficient amount of the gate voltage need to be provided. So there is a AC plus DC amount of the voltage that we have to provide. So the DC voltage of P DC that we have to provide, that also I'm considering as a parameter. Finally, we will give the all the values at a time. And amplitude also. amplitude. Let me take the parameter of amplitude as amplitude and the frequency 1 kilohertz. Yes, these three I'm going to select it over here, and RD as a parameter, W and L length also as a parameters I'm giving. So let me save this and let me launch AD Explorer, create new, okay, okay. So let me select the analysis type is transient. As we have given the frequency of the input is 1 kilo, 1 by 1 kilo is nothing but 1 milli. So I wanted to see the 3 cycles, so that I'm giving 3 milli over there as a stop time. So this is the transient analysis. And design variables, I have to select all the design variables which are already mentioned in the schematic. Amplitude of around 10 milli. As already mentioned that, as we have discussed that the short channel device will not be suitable for the analog application, so we will be keeping the large channel, I will be keeping it as a 1 micro. Yes, so initially RD value I'm keeping 1 kilo and VDC 700 milli, that is the DC voltage that we have to give it as a biasing. So this is the minimum voltage that transistor we can bring it out of the cutoff. So without the device, W by L I'm maintaining 10 times, W length what I gave it is 1 micro, and width I'm keeping it is 10 times. It is not mandatory as per the required value of the gain. When the transistor is up going into the linear, you can bring it back by the changes of the W. So we'll see that also. So now let me run. So I'm getting the phase shift. There should be 180 degrees phase shift for the input to the output. So if the phase shift is correct, functionally that circuit is operating. Whether you are getting the maximum gain or not, that we'll see it later on. So first of all, we have the input signal and output signal. And while you are calculating the gain, it is difficult to calculate the gain every time by considering the peak to peak of the input and peak to peak of the output. So for that, what I do is, so I will be bringing that V output send to calculator. So there in the calculator, I have the function name peak to peak, peak to peak. So the peak to peak of the V output will be calculated here. So let me send. So in the similar way, it will be sent to the AD window. So here you can see the peak to peak of the V output will be measured as expression over here. In the similar way, I can do the other thing also, the input peak to peak also we can measure. Send calculator. So peak to peak of the input also. Peak to peak of the input also. This we bring into the AD. So peak to peak of the input and peak to peak of the output. We can measure it over here. So as the peak to peak we are giving it is 20 milli, and so we'll be calculating the gain here. So this is the peak to peak of the V output. This is the peak to peak of the V output. This is the peak to peak of the V input. I will be dividing them, a peak to peak of output by peak to peak of the input, so that I can calculate it as a gain. So this is nothing but gain of the amplifier. So this is the practical gain. So we can calculate the theoretical gain also. So with the formula of Gm times of RL. So let us bring that. Let us get the values of Gm as well as Gm as well as RL. So RL is nothing but RT. But in few cases we have to consider that R output also. So let me bring the two parameters also into the AD window. Calculator. Operating point, and let me select my transistor. So I have to know the value of Gm. So let me bring into the ADL, and also R output also, and also I have to know the region of the transistor also. So let me take the region also. Yes, the region of the transistor also visible over here. So here this one. Yes. So these all things will be very helpful when you do the analysis. Let us do the simulation. So here it will be the value. So my gain of the amplifier is 1.083. It is almost once, like I'm not getting two times also. So whatever the input that I'm applying, almost the same kind of input that I'm getting it over here. So let me calculate the theoretical value. So here it is the formula wise that theoretically how can I calculate. So let me bring into the picture where that RD value what we have chosen is 1 kilo ohm. Let me keep that 1 kilo 1, and R output we got it. R output we got it around 74 kilo. So 74 kilo. So almost 74 kilo, which will be the very high value when it comes parallel with RD. As we already discussed, GM times of RD is the gain when we are when we are taking that R output in parallel with RD. So that value it will be calculated over here. So this is the RD parallel with VR output. RD parallel with R output, it will be calculated it over here. And the RS value, so here actually we are keeping RS in the next case. So as of now that RS is 0. So let me keep that 0. And the GM value what we got it is, GM value what we got it is, so here we can see that 1.093. So 1.093. 3. So if you get all these values, there is a formula that I already mentioned, gm times of this factor, gm times of rd parallel with r output. So as per the formula that we have already derived, so this is the formula that we have derived. So from that gm times of rd, so theoretically we can get the value of 1.78, 1.078. So theoretically we are getting the same also, the gain practically we are getting over here 1.083. So 1.083. So theoretically what we have calculated and practically what we have simulated and we got it, both are almost same. So now let us go with another case. So let us go with the 2 kilo ohms that I am applying. So load resistance I am keeping it is 2, and also I keep different values, 3 kilo ohm, 3 kilo ohm, and 4 kilo ohm, 5 kilo ohm, 6 kilo ohm, 7 kilo ohm, 8 kilo ohm, 9 kilo ohm. As we are expecting, as the load resistance RT is increases, so we are expecting that we are getting more gain. So that's what we have to simulate it now. And while we are keeping that RD value maximum, while we are increasing that RD value, we have to consider this one also. We discussed this concept. So this is the concept where we cannot go to the value of the resistance to any when we cannot increase the resistance for there is a limit up to which you can increase. So at after particular value of the load resistance, what happening, the transistor may have a problem that go into the linear. So based on this condition where we are simulating the load resistance as different values, 1 kilo, 2 kilo, 3 kilo, 4 kilo, 5 kilo, 6 kilo, 7 kilo, 8 kilo, 9 kilo, 10 kilo. So we are simulating all these values. So let us simulate it. So you will be getting all these values here. So we can see. So first thing what we have to observe is we need to calculate the gain, but more than the gain, we need to bother about the region. So whether the region of the transistor is it in 2 means it is in saturation, 1 means it is going into the linear. So when it is in the region 2, until which we don't have any problem. So when we are keeping load resistance is 2 kilo ohms, the transistor still it is operated in the saturation. 3 kilo ohm it is operated in the saturation. 4 kilo also, 5 kilo also, 6 kilo also, 7 kilo also, 8 kilo also, 9 kilo, 10 kilo. So there is a problem when we are keeping the load resistance of 10 kilo. So as already discussed, if you keep on increasing the load resistance, there will be a problem that the current will be limited, so the transistor may go into the linear, so transistor cannot be used for the analog application, right? So the same problem we will be facing it over here in the last case when the load resistance equal to 10 kilo. So practically we cannot keep the load resistance of 10 kilo. If you wanted to keep the load resistance of 10 kilo ohm, what we have to do is, as already discussed as already discussed So here when we are simulating, we got the value of the load resistance maximum. It can be up to not 20, it is up to 10 kilo ohm. It up to 10 kilo ohm. So the moment when 10 kilo ohms is connected, the current is limited, which will be less than the value which is expecting. So now we have to make sure the transistor should be modified with the expected current of less than the previous one. So for that what I do is, this is the expected current. As we know, if the W value, if it is reduced, W value it is reduced, transistor may expect less than the previous value, so that the transistor may come into the saturation again, right? So here what we do is we can make some modifications across the transistor. We can do proper sizing by adjusting the W value so that we can expect the less current, so the transistor may be brought into the saturation, right? So we can do that. Yes, so we will try that. We'll try that. So now what I'm trying to do is the W value where I kept with the value of 10 micro. So now I'm keeping 8 micro. So now when W value is reduced, transistor will be expecting less current. So if I do the simulation now, yes. So the moment when we kept 10 kilo ohm, the transistor was going into the linear region. Now we can protect it. So for the load resistance of 10 kilo ohms also, my transistor is operated in the linear region, right? Operated in the saturation region, right? So now I got the gain of around 6.3. So I will be getting the maximum gain 6.3 as the maximum value of the load resistance is equal to 10 kilo. So now I have to make sure that one point should be very clear. So we are getting the different values of the gain. Yes. So as per the theoretical calculations that we have, let us cross verify the value of the gain for the load resistance of 4 kilo. So let me take that different values of the load resistance where I'm keeping 4k here, 4k here. This is the case. This is the case 4k, and R output we got it around 82. RS we are keeping it as 0. Source resistance, source we did not connect anything, so source resistance equal to 0. And the GM what we got it is 860 micro, 860 micro, so 0.860. So you will be getting the theoretical value of the gain is around 3.28. So practically we are getting 3.28. So practically and theoretically we are getting the same gain. So whatever the formula we have derived and the simulation results, what values are given, both are almost same. So now we have to go with the another case, and we have to discuss about the limitations of the common source amplifier. So coming to the limitations of the common source amplifier is, as we are increasing the load resistance, no doubt we will be having the maximum gain. Yes, so it is depending upon the load resistance. I don't have any problem. But there is another factor. It is also depending on GM, right? So gain is depending on GM. But what is GM? GM is nothing but a transconductance gain of the amplifier. As we know that GM is nothing but mu COXW by L into VGS minus VTH. VGS minus VTH. So if you do the derivation with respect to ID by dou ID by dou VGS, if you do it, you will be getting this one. So over here, what happening? VGS is nothing but the voltage which is applied at the gate terminal. So I can say that this is nothing but the V input. So now what is the problem here is, as the V input is changed, so GM value also fluctuated. So V input is changed every time GM is fluctuated. So the changes in the GM will changes the gain. So my system which I have designed, the gain of the system is not maintained constant. I couldn't maintain the constant. I couldn't maintain the gain constant. So that is the main issue that I will be facing with the common source amplifier. So my system is not at all stable. The gain is totally fluctuated. The gain is totally controlled by the GM. The gain is every time changed because of the value GM changes with respect to input. So now I have to solve that problem. I have to get the solution. So when you wanted to have a system with more stability, we have to make sure the feedback need to be connected. So here in the second case, this is the second case. Here we are going with the second case where RS resistor is connected at a source terminal, which will be acts like a feedback, so because of the feedback we can maintain the stability, so the gain will not be fluctuated much, will be fluctuated but it won't be much where in the first case with compared to the first case. So here let us do the calculation for the gain and we'll be doing the simulation for the second case also. What we have done it for the first case, we'll be seeing the second case also now, right? So now calculation of the gain, let me draw the small signal AC equivalent circuit once again where V input is applied it over here. Drain is connected with the source terminal, drain is connected with the load as it in the first case. But the problem is it is not connected to here because source was grounded, so RD is connected to the source. But here source is not connected to the ground, source is connected to ground, source is connected to the ground through RS resistance. This is the RS resistance. Yes, this will be my equivalent circuit. So here RD which is connected to the ground. Yes. So this will be my small signal AC equivalent circuit. This will be my small signal AC equivalent circuit. So let us do the calculation of the gain for the small signal AC equivalent circuit from this. So gain is nothing but, as we know, that V output by V input. So we'll practically calculate these values one by one. So as the GM times R output, let me neglect it initially, and GM times of VGS current will be conducted over here, as that VGS is nothing but GM times of VGS is nothing but VG minus VS. VG is nothing but V input. VG is nothing but V input, and VS is nothing but VS, right? Previously VS was grounded, so VGS is nothing but we take it VGS minus VGS is nothing but VG minus VS. VS was grounded there, so it is not grounded here. There is a small difference. So now the same amount of the current will be conducted over here, so I can calculate the VS is nothing but the current of GM times of V input minus Vs is conducted, this much current is conducted into the resistance of the device is Rs. Yes. So now if you take this one is V output, we are taking the V output across the drain terminal. So this is where I collect my output. So V output is nothing but the current which is flowing into this one into RD. Yes, if I simplify this one, so Vs into, so this Vs it will be coming this side as 1 plus GM times of Rs equal to GM times of into Rs. So from this Vs is nothing but GM into Rs times of V input by 1 plus GM times of Rs. So now if you calculate the V output, so V output is nothing but so minus of this quantity, so minus of GM times of V input minus Vs. So this will be conducted into this one. So now I can say minus GM times of V input minus Vs into RT. Yes. So now Vs is the dependent factor on V input. So I have to bring the relation of V output in terms of the V input. So I will be eliminating the Vs. So let me solve that. Gm times of V input minus Vs is the value that we got it, Gm times of Rs times of V input by 1 plus Gm times of Rs into Rd. Yes. So final value is, if you bring this one 1 minus Gm times of this one, Gm times of Rs and Gm times of Rs will be cancelled. So it will be the quantity of V input into Rs minus Gm by 1 plus Gm times of Rs. Sorry, this is Rd, so it will be the value of Rd by 1 plus Gm times of Rd. You will be getting this one. So this is nothing but V output. So now V output, you got it in terms of V input. If you bring that V output by V input, you will be getting the value of Gm times of Rd by 1 plus Gm times of Rs, we got it, minus. So now let us do the comparison. So this is the first equation over here. This is the first equation over here, and compared with the second equation, we compare that gain is depending on Gm, so which will be strong function of Gm, so that whatever the Gm change strongly changes the V input, G input, sorry, strongly controls the gain. So here the gain is function of Gm, right? It's also a function of Rd, that is, you keep it as it. So gain is a function of Gm into the function of Rd. So here the gain is function of Gm by 1 plus Gm times of Rs. So this is the difference. So as the Gm is changed by 10%, the gain is also fluctuated by 10%. Gm is changed by 20%, gain is also fluctuated to 20%. So as the changes there, we have it across the Gm with respect to V input, the gain is also fluctuated that much, because it is a strongly function of the Gm. But here, if you keep the Rs resistance over here, this is nothing but feedback, the system is becoming more stable, because the gain is not a strong function of Gm, it is a function of Gm by 1 plus Gm times of Rs. So if it is 10% rise, so this denominator also rise by that much, right? So that there will be compensation will happen, the gain Gm of the numerator and the denominator Gm may get compensation, so that my gain is not a strong function of the Gm itself. So my gain may be maintained, some amount of the gain maintained constant, so not like the variations which we have it in the first case won't be having that many variations with respect to changes of the V input due to the changes of the Gm also. So this is what we have to prove it. So now what we do is, we will be changing the V input over here. So with respect to changes of the V input, if let us suppose V input equal to 20 millivolts, if you are giving like a 700 millivolts, so the gain might be, we are getting around a 6. If I am keeping 800 millivolts, so input is changed, so that Gm will also changed, so the gain will be increased to 7. So as that V input changes, the gain, we are expecting that constant for any value of the input, the gain should be constant, but is not maintained constant. That is a basic problem that we have. So that is the reason why we are going with the second case, common source amplifier with the source degeneration. So now we'll be doing the simulation in what way the gain is not maintained constant. So with the value of Rs, with the adding resistance of Rs, will it be gain maintained constant or not, we have to verify. Yes. So now, so previously we didn't have the load resistance. Now the common source amplifier will be modified. Here I'm keeping the source resistance. I'm keeping the source resistance. So the variable name for that resistance is considered as RS. So save it. RS resistance 1 kilo ohm. Let me connect. Now the load resistance what we got it around let's suppose the load resistance of 10 kilo, we got it value of the gain is around 6.3. So let me note down the gain which we got it is 6.3 for load resistance of 10. So this is 10, our output is 38, 38, gm is gm is 19.9, sorry 0.8 not 802. So I got the gain of 6.3. So now let me keep the load resistance as maximum that we got it 10k. So let me fix that load resistance 10k. So now I'm not varying the load resistance as the variations of the load resistance point of view. What is the changes in the gain that we have observed? Now what are the changes with respect to the GM change? Let me explain it over here. With respect to RT change, we observe the gain. RT it is increased 1 kilo ohm, 2 kilo ohm, 3 kilo ohm. As we can see that 1 kilo ohm you got it gain 1, 4 kilo ohm we got it nearby 4, 10 kilo ohm you got it nearby 6.3. As that RT value increases, a gain also increased, right? So now there is a fluctuations with respect to the changes of RT where the reflected gain how it is changed, that's what we observed. So practically that is correct. But when the V input is changed, when the V input is changed, as I said, V input is changed, GM will be changed. So if the GM is fluctuated, so the fluctuations in the GM will reflect it over there in the gain changes. So gain will be fluctuated with respect to GM. That's what we have to observe now. So further sake, what I do is I will be changing the VDC. So here that 700 milli, I'm keeping it as 800 milli. Yes, I will be changing the VDS. I'm changing the VGS value so that V input value so that GM will be changed, and also I have to observe that how the gain is changed. First thing is we have to verify whether the transistor is in the linear region. 500 milli is 2, 2, 2, everywhere 2. So for all the values of the VDC, for all the inputs, the transistor is operated in the saturation region, so we don't have any problem. So what happening? So let me see the waveforms. Region I don't bother because for all the cases the transistor is operating in the second region. So let me delete. Let me delete this one. GM. What happening in the GM value? The input, the output, gain practically. So what happening? As the V input changes, the gain is also changed, right? But what we are expecting, the gain should be constant. So there should not be gain, right, which varies like this. We are expecting what? The gain should be constant. So here the problem is as the input VGS changes, as the VGS changes, as the VGS changes, P input changes, GM will be changed. So that GM when it is changed, the gain is changed. So the same thing we can see it over here in the simulation. So as the V input changes, GM is also changed. So that practically the gain is also changed. Yes. So now what I'm trying to do is the feedback resistance of 1 kilo. Instead of that, if I'm keeping it as 8 kilo ohm, so that feedback value once it is increased, system will be becoming more stable. So now if I do the simulation once again, so in all the cases the transistor is operated in the region 2, so I don't have any problems. I can verify the simulation results. uh, I don't bother about the V input, I don't bother about region because all the cases where the transistor operated in the second region, so I don't bother. R output also is not required, V output is also not required. Yes, you see, so when Rs equal to 1 kilo ohm, so there is a value of VDC input is 0 0.4, V input is 0 0.5, V input is 0 0.6. As the V input changes, right, different values of the V input, there is a gain. Practically we can see the gain is at one level, at another level, at another level, at finally over here, right? So there is just so much fluctuations over there. The gain is changed from here to here. So further changes of the V input due to the changes of the GM. So as we can see, this is the dependency. As we know, the V input is changed from 0 0.4 to 0 0.8. So the GM value is changed by this much. GM value is changed by this much. When where in the case of Rs equal to 8 kilo ohms, it is not changed by that much. There is no much fluctuation. If you keep on increasing the Rs value instead of 8 kilo ohm, if you are keeping it as 10 kilo or 15 kilo, so the fluctuations will be very less. So the GM changes will be very less. So as the GM value is very less, changes of the GM is very less. So we gain changes also very less. So if the system gain is not changed much, then system will be called as a stable one, right? So we have to make sure the system has to be very stable upon the variations of the gain is very less when we are keeping the source resistance is maximum. So this is the uh, final simulation. As the resistance of Rs we are keeping it maximum, you will be maintaining the gain almost constant. For all the changes of the V input, all the changes of the GM, you are maintaining the gain is almost same. For all the levels it is almost same. But the problem is you will be getting the gain is very less. So we can overcome that issue where the gain is very less by this one. So where we can see where we can see so the GM times of Rs, if it is very high, if we consider, So the moment when RGM times of RS is very high, so 1 can be neglected. So the moment 1 can neglect, GM get cancelled. So that my gain is totally depend on RD and RS. So minus n will be there. So as you maintain the ratio, if RS equal to 10 kilo ohm you are connecting, so you have to maintain that ratio. So how many times that RD need to be? So based on the requirement of the gain. So if you increase that RD, you can maintain the gain maximum. So where like we are getting the gain minimum over here in this case practically. So gain is nearby 1 or 2, so around 1. So we can increase it by increasing the load resistance.